Right now, somewhere in the space between our solar system and the next star over, a planet the size of Earth may be drifting through absolute dark, with no sun ever rising over it. Astronomers now suspect worlds like this could be more common across our galaxy than the ones that still orbit a star. But here is what most people get wrong about a rogue planet. It is not a world that broke away from its sun. Some were never close enough to lose one. They may never have had a star at all. If you enjoy deep space and science content, do me a small favor, hit that like button and subscribe. It genuinely helps this channel grow, and there is much more like this coming. Make yourself comfortable. Let's begin. Long before anyone photographed a rogue planet, theorists had already stopped assuming a planet needed a star to exist. Computer models of forming solar systems, built through the 1990s, kept producing an awkward byproduct almost nobody had gone looking for. Planets flung loose from their systems entirely, left to drift with no sun at all. Most researchers treated it, at first, as a strange quirk of the simulations, rather than a real population waiting somewhere in the sky, an artifact of imperfect code, rather than a genuine feature of how solar systems are actually built. Nobody had a telescope pointed at the right target to say otherwise, and for a while, the idea sat quietly in journal footnotes rather than headlines. That assumption changed in the year 2000, quietly, in two observatories that did not know the other was looking. In Hawaii, a British team led by Philip Lucas and Patrick Roche pointed a telescope called UCURT toward the Orion Nebula, a stellar nursery roughly 1,300 light-years from Earth, where thousands of young stars are still being born inside clouds of gas and dust. The light reaching their telescope had left that nebula around the year 700, more than 1,000 years before anyone built an instrument capable of catching it. The team was not hunting for planets. They were cataloguing faint, cool objects scattered through the nebula, and most of what they found behaved exactly as expected. Dim young stars, slowly contracting, slowly heating. But a handful of objects did not fit. They were too cold and too faint to be stars of any age, and careful follow-up ruled out the obvious alternative, that they were simply distant background stars seen by chance in the same direction. In simple terms, the team had found things with planet-sized masses, sitting completely alone, with nothing nearby large enough to call itself their sun. Their findings were published that year in the monthly notices of the Royal Astronomical Society. Around the same time, on the other side of the world, a Spanish team led by Maria Rosa Zapatero Osorio was studying a cluster called Sigma Orionis, a grouping of young stars a little over 1,000 light-years away. Using the Keck telescope, her team identified 18 faint red objects that seemed to belong to the cluster, but circled no star within it. Follow-up spectroscopy confirmed that some of these objects weighed only a handful of times the mass of Jupiter, small enough to fall below a very specific boundary that separates a planet from a star that simply never lit up. The team's paper appeared in the journal Science that October, under a modest title that gave no hint of how strange its subject truly was. That boundary has a name, the deuterium burning limit, and it is easier to picture than it sounds. A true star ignites ordinary hydrogen and keeps burning for billions of years. A brown dwarf, sometimes called a failed star, never gets hot enough for that, but it is heavy enough to briefly fuse a rarer, heavier form of hydrogen called deuterium before that fuel runs out. Below roughly 13 times the mass of Jupiter, an object cannot ignite anything at all, not even briefly. It can only sit there, radiating away the heat left over from its own birth, cooling year after year toward the temperature of the space around it. Anything under that line, drifting free with no star nearby, fits the loose definition of a rogue planet. Two teams, working continents apart, with different telescopes and no knowledge of each other's results, had landed on the same conclusion within months. Worlds without stars were not a theoretical curiosity dreamed up by physicists. They were sitting in the data the entire time, waiting for someone to look closely enough to notice them. None of this settled what to actually call these objects, and the disagreement over naming has never fully gone away. Astronomers writing careful papers still tend to favor a longer, drier phrase, free-floating planetary mass object, precisely because it avoids taking a position on how the thing came to be alone. The public, understandably, preferred something shorter. Rogue Planet carried a hint of story to it, of a world that had gone somewhere it was not supposed to go, and the name stuck in popular use long before scientists agreed on what these worlds actually were. That gap between the tidy public name and the messier scientific reality runs through this entire subject, and it is worth remembering as this becomes stranger. For the next decade, discoveries like these stayed rare because they depended on one narrow circumstance. A newly formed rogue planet still glows faintly with leftover heat from its own collapse, which makes it detectable by infrared cameras, but only while it remains young. An older rogue planet, cooled for billions of years, gives off next to nothing. Finding one of those required an entirely different method, one that does not depend on catching a planet's own light at all, but on catching what its gravity does to somebody else's. That method is called gravitational microlensing. Mass bends light, a consequence of general relativity that Einstein worked out on paper long before anyone had the instruments to see it happen. If a planet, even a cold and starless one, happens to drift almost exactly between Earth and a distant background star, its gravity acts briefly like a lens, magnifying that star's light for a matter of hours or days before fading back to normal. The odds of catching this alignment by chance are close to nothing. Watching a single star for a rogue planet to pass in front of it would mean waiting, on average, close to 1 million years for one useful flicker. The planet responsible is never seen directly. It is inferred entirely from the flicker it leaves behind, a flicker that happens once and will not happen again in any of our lifetimes. In 2011, a Japanese-led collaboration called MOA, working alongside the long-running OGL survey, published a result that made headlines well beyond astronomy. Using a telescope at Mount John Observatory in New Zealand, the team had quietly been watching 50 million stars toward the crowded center of our galaxy. Counted one at a time, at a rate of 1 star every second, 50 million stars would take close to 1.5 years just to look at once. Buried in that data, the team found a cluster of unusually brief flickers, and their analysis suggested something startling. Rogue, Jupiter-sized planets, they proposed, might outnumber ordinary stars in the Milky Way by roughly 2 to 1. For a moment, it seemed our galaxy might hold more starless worlds than it had suns to warm them. That number did not survive contact with more data, and this is where the story becomes, if anything, more honest. A 6-year follow-up campaign by the OGL survey, completed in 2017, examined thousands of additional events and found nothing close to that ratio, placing the true rate for Jupiter-sized rogue planets far lower, somewhere near 1 for every 4 stars. Years later, a further reanalysis traced part of the original excess to a subtle distortion in how starlight bends, passing through Earth's own atmosphere. An instrumental effect nobody had accounted for the first time around. The bold early number had been, in part, an illusion of the equipment rather than the sky. In simple terms, the galaxy had not shrunk. Our instruments had simply learned to see it more clearly. But underneath that correction, something smaller and stranger was still there. In 2016, a joint Ogle and Korean telescope network caught a flicker lasting only 41.5 minutes, the shortest microlensing event ever recorded. The briefness of an event is itself a kind of measurement, since the less massive the object, the faster its gravity sweeps past, and the shorter the flicker it leaves behind. When astronomer Przemek Mróz and his team modelled this 1 year later, the numbers pointed to something between the mass of Mars and the mass of Earth, with no companion star anywhere within 8 times the distance from our Sun to our own Earth, farther out than Saturn's orbit. Consider what that means. An object smaller than our own planet, alone in the galaxy, betrayed its existence through a brightening of starlight that lasted less time than a lunch break and was never seen before or since. 2 decades after Lucas, Roche and Zapatero Osorio first noticed something drifting alone inside a stellar nursery. The picture is neither fully confirmed nor closed. The giant Jupiter-class population that made the original headlines turned out to be smaller than first claimed. But in its place, a quieter and perhaps stranger population has emerged. Smaller worlds, harder to catch, possibly far more numerous than anyone expected when this search began. Every one of them, giant or small, shares the same basic fate. No sunrise, no sunset, no warmth arriving from anywhere outside itself. Only the slow keeping of whatever heat it was born with. Some of that heat, as it turns out, may last far longer than anyone assumed 20 years ago, which is itself a thread worth returning to later. Naming these worlds and beginning to count them, though, only answers part of the question. It does not explain how a planet ends up alone in the first place, whether it was cast out of a family it once belonged to, or whether it was never claimed by one at all. Those two histories would leave behind different kinds of worlds, and telling them apart means going back to the very beginning of how a solar system is built, long before it has finished deciding which of its planets it intends to keep. That question reaches back further, to the same violent, unsettled years that shape the birth of every solar system, including, it turns out, our own. 2 ways to be orphaned. It starts with a system that should never have survived its own childhood. Every solar system begins as a disk of gas and dust circling a newborn star, and inside that disk, planets do not simply settle into their final orbits and stay there. They jostle. Early in a system's life, giant planets in particular can find themselves too close together, close enough that their gravity begins tugging on one another instead of only on the star. Over millions of years, that tugging compounds. Orbits stretch, orbits tilt. What began as a tidy, nested arrangement of planets can turn into something closer to a slow-motion collision course, playing out not over seconds, but over the better part of 100 million years. Our own solar system may not have been an exception to this. A body of research nicknamed the Nice model, after the French city where it was developed, proposes that the outer solar system's 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in the orbits they occupy today. Instead, gravitational interactions between them and a disk of leftover debris caused their orbits to slowly migrate. And at some point in that migration, the system briefly became unstable. Some versions of this model go further, suggesting that our solar system may once have held a fifth giant planet, one that no longer exists in any orbit at all, because it was thrown out entirely during that instability. In simple terms, the solar system you were born into may have started as a 5-player game and gambled one of its own away before anyone existed to watch it happen. This is the essential mechanism behind planetary ejection, and it applies far beyond our own case. In a multi-planet system, gravity is never a simple, closed arrangement between a planet and its star. Every other planet in that system is also pulling, faintly but constantly, and over enough time those faint pulls can add up to something decisive. Astronomers model this using what's called n-body simulations, essentially running a solar system forward in a computer millions of times with slightly different starting conditions, to see how often things stay stable and how often they don't. The results are consistently uncomfortable. A meaningful fraction of simulated systems end in ejection, one planet gaining enough momentum from its neighbor's gravity to simply outrun the star's ability to hold onto it. There's a specific threshold that decides whether a planet stays or leaves, and it comes down to a comparison of two speeds. Every star has what's called an escape velocity at any given distance, the speed an object would need to reach to break free of that star's gravity entirely rather than eventually falling back. If a series of gravitational encounters with other planets accelerates a world past that threshold, it doesn't matter how big or bright the star is. The planet leaves, and it does not come back. Consider what that means in practice. The same star that spent millions of years slowly building a planet, layer by layer, out of the material orbiting it, has no ability whatsoever to reel it back in once it crosses that line. Gravity, for all its patience, has no reverse gear. The timing of this matters too. Ejections overwhelmingly happen early, typically within the first few 100 million years of a system's life, while the orbits are still settling and giant planets are still close enough together to interact strongly. A system that survives its first several 100 million years relatively intact tends to stay that way for billions of years afterward. The same way a building that survives its first earthquake without cracking is likely to remain standing through smaller aftershocks, which means that somewhere out there, right now, there are almost certainly young systems in the middle of losing a planet, the ejection already underway, the outcome already decided by physics, even though the planet in question hasn't technically left yet. But ejection is only one half of this story, and for a long time, astronomers assumed it was the whole explanation for every starless world. That assumption turned out to be wrong. Some rogue planets, it now appears, were never part of a family to begin with. They form the way a star forms, through the gravitational collapse of a cloud of gas and dust. Except the collapse simply runs out of material before it can ignite anything. Deep inside star-forming regions like the Orion Nebula, astronomers have found objects only a handful of times the mass of Jupiter, isolated, with no evidence of ever having belonged to a planetary disk around a star at all. Their formation looks less like a planet that was built and then exiled, and more like a star that was attempted and simply fell short. This distinction matters more than it might first seem. An ejected planet carries a history. It likely formed close to a star, in a disk rich with the same rocky and metallic material that built Earth, before violence sent it outward. A planet born in isolation carries no such history. It condensed directly from the cold outer material of a collapsing cloud. the same raw ingredients that would have built a star if there had simply been more of them. Two objects can end up drifting through the same patch of galaxy, both starless, both dark, and yet arrive at that condition by what are essentially opposite paths. One cast out, one never brought in. Telling these two populations apart from a distance is extraordinarily difficult, and in most individual cases, astronomers genuinely cannot do it yet. A cold, dark object with no companion star doesn't advertise its own origin story. What it carries instead are subtler clues: its mass, sitting either comfortably within planetary range or dangerously close to the deuterium-burning boundary that separates a planet from a failed star, and its composition, if it can be measured at all, hinting at whether it formed close to a star's heat or far out in the cold. Neither clue is definitive on its own. Together, they are the closest thing astronomers currently have to a birth certificate for a world with no sun. What this means is that rogue planet was never really one category of object. It's a shared condition, isolation, arrived at by at least two entirely different histories, one of belonging and violent loss, the other of never belonging at all. Somewhere in the galaxy tonight, both kinds are drifting, indistinguishable to the eye, carrying two different kinds of silence. And once you accept that these worlds exist and understand roughly how they come to be alone, a harder question follows immediately behind it. How, with no light of their own to search for, do you go about finding something that was built, in every sense, to be invisible? Finding the invisible. It starts with a plain, blunt fact about how these searches actually work. You cannot point a telescope at a rogue planet the way you'd point one at a star, because there is nothing there to catch. No starlight to reflect, no steady glow to track night after night. For older rogue planets, the ones that formed billions of years ago and long since radiated away their birth heat, there is effectively no light at all, in any direction, at any wavelength worth searching. Astronomers had to accept a strange premise before this search could even begin. They would need to find something by the absence it created, not by anything it gave off. The tool that makes this possible is gravitational microlensing, and the underlying idea comes directly from general relativity. Mass curves the space around it, and light traveling through curved space bends along with it. A planet, even a completely dark one, still has mass, and that mass still bends light passing near it. If a rogue planet happens to drift almost exactly between Earth and a distant background star, its gravity briefly acts as an imperfect lens, magnifying and brightening that star's light for a short window of time before everything fades back to normal. In simple terms, you are not looking for the planet. You are looking for what the planet does to somebody else's light on its way to you. This method comes with an unusually strict cost, and it's worth sitting with before the numbers arrive. A microlensing event is not repeatable. Once a rogue planet passes in front of a background star and produces its telltale brightening, that alignment is gone. The planet keeps moving, the star keeps moving, Earth keeps moving. The three of them will likely never line up again in any human lifetime, and possibly never again at all. There is no second observation, no way to point a bigger telescope back at the same event next month for confirmation. Whatever data you collect during those few hours or days is the only data you will ever get. That constraint shapes everything about how these surveys operate. Instead of watching one patch of sky closely, projects like OGLE and MOA monitor tens of millions of stars simultaneously, night after night, for years at a stretch, essentially running a permanent, wide-angle stakeout of the crowded central bulge of our galaxy, where stars are densest and the odds of a chance alignment are highest. Most nights produce nothing unusual. The value of the survey lies entirely in its patience, in the accumulated years of watching, waiting for one of those tens of millions of stars to flicker in exactly the right way. The shape of that flicker is itself a measurement, and this is where the physics becomes genuinely elegant. The duration of a micro-lensing event depends directly on the mass of whatever caused it. A star passing in front of a background star produces a brightening that can last for weeks. A planet, being far less massive, sweeps past much faster, producing an event lasting only hours, or, in the most extreme cases, minutes. Astronomers can look at nothing more than a brightness curve, a simple graph of light intensity over time, with no image of the object itself anywhere in it. And from the width of that curve alone, estimate roughly how much mass caused it. A wide curve points to a star. A narrow curve points to something planet-sized. An extremely narrow curve points to something smaller still. There's a second measurement hidden inside these events that sharpens the picture further, something called the angular Einstein radius. Without getting lost in the mechanics of it, this measurement helps astronomers judge not just how long an event lasted, but how the brightening rose and fell in detail, which in turn constrains both the mass of the unseen object and, in some cases, how far away it likely is. Events where this detail can be measured are rare and valuable, because they turn a rough mass estimate into something closer to a real one. Even with these tools, distinguishing a genuinely starless planet from one that simply has a very distant, very faint companion star remains difficult. When astronomers detect a short micro-lensing event, they can often rule out a companion star within some radius, based on how the brightness curve behaves, but they usually cannot rule one out entirely. Consider what that means in practice. Most of the objects labeled rogue planets in these surveys are, more precisely, planets with no companion star detected within the range the data allows, which is a narrower and more honest claim than the label suggests, even if the label itself has stuck. The survey work being done right now is only the beginning of what this method is capable of. Ground-based telescopes like the ones used by OGLE and MOA are limited by Earth's atmosphere and by the simple fact that they can only watch the sky when it's dark, clear, and pointed the right direction. A space telescope, watching continuously from above the atmosphere, could catch dramatically more of these fleeting events, including ones far too faint or far too brief for any ground-based instrument to register. That next generation of searching is already being built, and what it may reveal about the true scale of this population is a thread this script will return to. For now, what these surveys have already established is enough to sit with on its own. Somewhere above the galactic bulge, tens of millions of stars are being watched patiently for a flicker that might last less than an hour. Each flicker is a planet's entire visible signature, its only appearance in our data, its one and only moment of being findable at all. And once you understand how thin and fleeting that evidence really is, a different question starts to matter more than how we find these worlds. It's what waits on one, in the hours after the flicker fades and the world goes back to being alone in the dark, with no sun and no light of its own, and nothing to keep it warm except whatever it happens to be carrying inside itself. Strip away every source of heat a planet could possibly have, no star overhead, no internal warmth left over from its own birth. And what remains is not simply cold. It is close to the coldest temperature the universe permits anywhere. Left alone long enough, a truly inert world would settle toward roughly 2.7 Kelvin, the faint, uniform afterglow left over from the Big Bang itself, still bathing every corner of the universe nearly 14 billion years later. That afterglow, called the cosmic microwave background, is not a local phenomenon a planet could somehow shield itself from or drift away from. It is the temperature of space itself, everywhere, the true floor beneath which nothing in the observable universe naturally falls. In simple terms, a completely dead rogue planet would not just be cold the way a winter night is cold. It would approach the temperature of empty space itself, colder than anything achievable in an ordinary laboratory freezer, colder than liquid nitrogen, colder than almost anything you could construct on Earth without highly specialized equipment. At that kind of cold, an atmosphere does not simply thin out, it falls. Nitrogen, the gas that makes up most of Earth's air, turns to frost around -210 degrees Celsius. Oxygen follows shortly after, and carbon dioxide, methane, and every other common atmospheric gas eventually join it on the ground. Even the atmosphere of a rogue planet, if it had one, would eventually snow onto its own surface, layer after layer, until the entire sky it once had was lying frozen on the ground beneath it. Something close to this already happens, faintly, on distant worlds still inside our own solar system. Pluto and Neptune's large moon Triton, both far enough from the Sun that its warmth barely registers, show nitrogen ice fields and seasonal frosts that shift as their thin, remaining sunlight varies. A rogue planet takes that same process to its logical end, with no sunlight left to vary at all, and no season to eventually bring the frost back into vapor. A planet in this state would not merely be dark, it would be geologically silent, its surface a fixed, frozen photograph of whatever it happened to look like the moment its heat ran out. Not every rogue planet starts out this cold, and the timeline matters. A planet freshly ejected, or freshly formed in isolation, still carries the residual heat of its own violent birth. The same heat that let infrared telescopes spot the youngest free-floating worlds in star-forming regions in the first place. That primordial heat fades over tens to hundreds of millions of years. A genuine countdown, brighter and easier to detect early on, dimmer and harder to find as the planet ages. The way a dying ember cools fastest in its first hour and only slowly afterward. Radioactive decay does not fade the same way. Its half-lives run into the billions of years, uranium-238 alone taking roughly 4.5 billion years for half of it to decay, meaning a planet's radiogenic furnace keeps burning at something close to a steady rate, long after the heat of formation has bled away entirely. What this means in practice is that every rogue planet passes through two distinct chapters of warmth. A brief, brilliant one that gave astronomers their first glimpse of these objects, and a much longer, much quieter one, powered by nothing but decaying atoms, that persists for essentially the rest of the planet's existence. But this bleak baseline assumes something that is often not true, that a rogue planet has no heat source of its own. Most do. The same process that keeps Earth's interior molten today, billions of years after our Sun first lit up, has nothing whatsoever to do with the Sun. It comes from radioactive decay, the slow, steady breakdown of elements like uranium-238, thorium-232, and potassium-40, locked inside a planet's rock since the moment it formed. Earth's interior currently radiates about 47 trillion watts of heat this way, roughly half of it from that radioactive decay alone, and the other half left over from the sheer violence of the planet's original formation, heat that has simply never finished escaping. Spread across the entire surface, that works out to less than 1/10 of a watt for every square meter of ground. A trickle compared to sunlight, and yet enough, given billions of years and nowhere else for it to go, to keep an entire planet's interior from ever fully going cold. Consider what that means. Somewhere under your feet right now, atoms are splitting apart and releasing energy, in a process utterly indifferent to whether a star exists overhead at all. A rogue planet keeps that furnace. It just loses the one on top. This is where a genuinely strange hypothesis enters the picture. In 1999, planetary scientist David Stevenson proposed that an Earth-sized rogue planet, if it happened to retain a sufficiently thick atmosphere of hydrogen, could use that internal heat to keep liquid water on its surface, with no sunlight involved at all. He estimated that an Earth-mass planet could plausibly hold onto a hydrogen envelope amounting to somewhere between 0.1% and a full 1% of its total mass. A thin sliver by planetary standards, but more than enough, at sufficient pressure to do the job. The mechanism relies on a property of hydrogen gas under enormous pressure. Thick enough, a hydrogen atmosphere becomes remarkably good at trapping far infrared radiation, the kind of heat a planet's own interior constantly leaks outward. Rather than escaping into space, that heat gets bounced back downward again and again, the same way a blanket does not generate warmth so much as refuse to let the warmth you already have escape. In simple terms, the planet would not need a sun. It would only need to stop losing the heat it was already making for itself. There is an obvious catch, and it is worth stating plainly rather than glossing over it. Young stars are aggressive. Their ultraviolet light and stellar wind tend to strip lighter gases like hydrogen and helium away from any nearby planet fairly quickly, which is why Earth, still orbiting an active sun, has essentially none of its original hydrogen envelope left. A rogue planet ejected early enough, before its star had the chance to finish that stripping, might carry its primordial atmosphere with it out into the dark, fully intact, protected from the one process that would have destroyed it. The violence that exiled the planet may, in a narrow and almost accidental way, be the same violence that preserved the blanket keeping it warm. Even where a thick hydrogen atmosphere never develops or never survives, there is a second, more modest path to warmth, one with a working example already sitting on Earth. Beneath roughly 4 kilometers of Antarctic ice, Lake Vostok has remained liquid for millions of years, entirely without sunlight, kept from freezing solid purely by the same geothermal heat rising from below. Ice, it turns out, makes a surprisingly effective lid for this purpose. It conducts heat poorly compared to rock or water, which means a thick enough shell can hold a temperature gradient across itself for a very long time, cold and frozen on the outward-facing surface, warmer and liquid on the side pressed against the planet's interior. Researchers Dorian Abbott and Eric Switzer proposed in 2011 that an Earth-sized rogue planet could work the same way on a larger scale, an entire world wrapped in a shell of surface ice, its heat trapped not by a thick atmosphere, but by the ice itself acting as an insulating lid, with an ocean of liquid water sealed underneath, warmed only by the planet's own radioactive decay. They gave this scenario a fitting name, the Steppenwolf, after the lone wolf of the title, a world with no pack, no sun, and no light of any kind reaching its hidden ocean ever. It is worth being honest about how far ahead of the evidence this idea currently sits. Nobody has detected a subsurface ocean on a rogue planet, and given that these objects cannot even be directly imaged in most cases, only inferred from a single flicker of borrowed starlight, that kind of detection remains well beyond what current instruments can attempt. The Steppenwolf hypothesis is a calculation about what the physics permits, built from known values for ice conductivity and radiogenic heat output, not a discovery about any specific world. That distinction matters, and it is one this script intends to keep honoring, rather than blurring for effect. There is a further twist that applies to some, though certainly not all, of these worlds. Not every planet leaves its solar system alone. Simulations of planetary ejection show that a planet can sometimes carry a moon along with it, during the same violent instability that throws it clear of its star. The moon's own orbit disturbed just enough to follow its planet outward, rather than being flung off on a separate path entirely. Researchers John Davies and Stein Sigurdsson calculated in 2007 that the gravitational flexing between an ejected planet and its surviving moon, the same kind of tidal stress that keeps Jupiter's moon Io volcanically active today despite Io's own enormous distance from any sun, could boost that planet's internal heat output by up to 100-fold, for roughly 100 million years after the ejection itself. That is a geological blink of an eye, not a permanent condition, a window that eventually closes as the moon's orbit settles and the flexing calms. But for a while, a planet in that situation would be running distinctly warmer than a lone world of the same size and age, heated not by starlight and not only by its own radioactivity, but by the gravitational company it happened to keep on its way out into the dark. None of this amounts to a hidden garden waiting in the dark. Nothing here suggests these are pleasant places or even survivable ones by any standard familiar to us. What it means is narrower and, in its own way, more interesting. Dead is not automatic. A world with no star can still be generating real heat, sealing that heat beneath an ocean or an atmosphere, running a slow furnace lit entirely by its own decay, with no help from anything outside itself. Whether any actual rogue planet meets the specific conditions these models describe remains entirely unconfirmed. What has been established is only that the physics does not forbid it, which, for an object this isolated, this dark, and this far beyond the reach of any telescope built so far, is already a great deal to say. Enough theory has been built now to ask what should have felt obvious from the very beginning. If some fraction of these starless worlds could plausibly be warm inside, sealed, quiet, and slowly cooking beneath their own ice, then the question of how many of them actually exist stops being a curiosity and starts being something closer to a question worth answering carefully, one that reaches all the way from a single flicker of borrowed starlight to an estimate of an entire galaxy's worth of worlds nobody has ever seen. How many are out there? It starts with an uncomfortable admission that has nothing to do with telescopes at all. By the International Astronomical Union's own working definition, most of the objects discussed so far in this script are not, technically, planets. In 2003, a working group within the IAU tried to settle what to call these starless bodies, and the answer they landed on was almost apologetic in its caution. An object below the deuterium burning limit that orbits a star, they agreed, is a planet, regardless of how it formed. An object above that limit is a brown dwarf, wherever it happens to sit. But a free-floating object in a young star cluster, below that same mass limit, orbiting nothing at all, is neither. The working group called it a sub-brown dwarf, adding almost as an aside, or whatever name is most appropriate, a phrase that reads less like a confident ruling and more like scientists quietly admitting they had not fully solved the problem. In simple terms, the very worlds this script has spent an hour describing do not, by the field's own official language, fully qualify for the name most people already use for them. The word rogue planet survives because it is useful, not because it was ever formally approved. This is not simply bureaucratic hair-splitting. It reflects a genuine, unresolved argument. Even the IAU's better-known 2006 definition, the one that reclassified Pluto, technically applies only to objects orbiting our own sun, leaving every planet around every other star in the galaxy formally undefined by the same document, let alone the ones orbiting nothing whatsoever. Astronomers have proposed updated definitions since, ones that would extend planetary status to objects orbiting other stars, brown dwarfs, or stellar remnants. None of those proposals have been fully adopted. In the meantime, researchers writing actual papers about these objects have quietly generated more than a dozen competing names. For the same basic thing, cluster planet, nomad planet, orphan planet, wandering planet, starless planet, isolated planetary mass object, each one favored by a different research group for slightly different reasons, none of them universal. What this means in practice is that the naming problem raised earlier in this script, the gap between the tidy public term and the messier scientific reality, was never a minor footnote. It sits at the very center of how seriously the field takes this population, and how confidently it can even begin counting them. Counting them, despite the naming trouble, is exactly what astronomers have spent the last several years trying to do, and the most recent attempt did not come from micro-lensing at all. In 2023, using the James Webb Space Telescope, astronomers Mark Makorian and Samuel Pearson surveyed the inner Orion Nebula and the Trapezium cluster, the same general neighborhood where Lucas, Roche and Zapatero Osorio had made their original discoveries more than 2 decades earlier. What they found went well beyond a simple update to the census. Among more than 500 Jupiter-mass, planet-like objects drifting free with no star, roughly 1 in 10 turned out not to be alone after all. 42 of them were paired off, 2 starless worlds orbiting each other directly, bound only to one another, with nothing else nearby heavy enough to call itself a sun. Astronomers gave these pairs a deliberately memorable name, Jupiter Mass Binary Objects, or JUMBIOs, and even that slightly playful acronym could not disguise how genuinely strange the discovery was. Consider what a jumbo actually requires to exist. 2 objects, each somewhere between roughly half and 14 times the mass of Jupiter, need to end up gravitationally bound to each other, sometimes separated by as much as 384 astronomical units, nearly 10 times the distance between our Sun and Pluto, with no star involved in binding them together at all. That is not a tight, cozy pairing. It is 2 dark, sunless worlds, each capable of drifting apart entirely under the slightest additional disturbance, somehow holding on to one another across a gap that would swallow our entire solar system twice over. Wide, sunless pairings are not entirely without precedent. Astronomers have previously found brown dwarfs, the true failed stars, 1 tier up in mass, orbiting each other at similarly extreme separations. So the basic idea of 2 dim, starless bodies keeping each other company is not new. What is new, and what nothing in the leading theory of planetary ejection predicts easily, is finding it this far down the mass scale, among objects light enough to be called planets by nearly every definition on that competing list of names. A planet violently thrown out of its system does not usually drag a second planet along with it in a neat, stable, mutual orbit. The leading explanation instead borrows directly from star formation itself, the same process that produces binary stars in the first place, scaled down to objects that never grew large enough to ignite. If that explanation holds, then a meaningful fraction of the free-floating population in this survey was never part of a planetary system at all. Not exiled, not orphaned, simply born this way, in pairs, the way some stars are. It is worth pausing on how unsettled this finding still is, because that honesty matters more here than almost anywhere else in this script. In 2024, astronomer Kevin Luhman published a challenge to the jumbo interpretation, arguing that at least some of these objects could be nothing more exotic than distant, reddened background stars, misread by the survey's methods. The debate has not been resolved. Follow-up radio observations of one specific pair, catalogued as Jumbio 24, detected a faint, steady radio signal in 2024 and 2025 that is difficult to explain if the objects are ordinary background stars. But the mechanism behind that signal remains, in the researchers' own words, a genuine mystery. This is a live scientific argument, not a settled fact being smoothed over for the sake of a good story. Alongside the puzzle of what these objects are sits the much larger question of how many of them exist, and the most promising answer to that question is not yet in hand. It is currently sitting inside a spacecraft. The Nancy Grace Roman Space Telescope, NASA's newest flagship observatory, is scheduled to launch on August 30th, 2026, less than 2 months from when this was written, on a Falcon Heavy rocket bound for a position roughly 1 million miles from Earth. Unlike the ground-based surveys described earlier in this script, Roman will watch the galactic bulge continuously, from above the distorting effects of Earth's own atmosphere, for years at a stretch, carrying a field of view roughly 100 times wider than the Hubble Space Telescopes, while matching Hubble's own sharpness. Free-floating planets are only one item on a long list of things it was built to find, alongside dark energy, distant galaxies, and, almost as a side note, isolated black holes drifting through the galaxy in a way not unlike the planets this script has spent an hour describing. Earlier projections, based on the assumption that rogue planets are roughly as common as ordinary starbound ones, suggested Roman might catch around 50 Earth-mass free-floating planets over its 5-year mission. A newer analysis, published in 2023 by astronomer Naoki Koshimoto and colleagues, revised that number upward by a factor of 8 to somewhere near 400, built on the growing evidence that smaller, Earth-sized rogue worlds are considerably more common than the giant, Jupiter-class ones that first made headlines back in 2011. In simple terms, the telescope that will finally test this population directly is not decades away. It is, as of this recording, already sitting on a launch pad. It is worth stepping back and tracing how far that specific number has traveled. This script opened its history with a claim that Jupiter-sized rogue planets might outnumber stars 2 to 1, a claim that was later walked back to something closer to 1 rogue world for every 4 stars, and smaller besides. Now, more than a decade after that original overreach, the pendulum has swung back in a different direction, not toward the giant planets that made the original headlines, but towards smaller, Earth-sized worlds that earlier surveys were never sensitive enough to catch in meaningful numbers. Each revision has looked, briefly, like a correction that shrinks the population. Each time, something smaller and harder to see has turned up, hiding underneath the number that was revised downward. That pattern itself is worth sitting with. It suggests the honest answer to how many of these worlds exist has consistently been larger than whatever the most recent, most cautious estimate allowed for. Put every piece of this together, and a genuinely strange picture starts to take shape. A body meant to define what a planet is has never quite settled on what to call these objects. A single infrared survey of one nebula turned up hundreds of candidates and an entirely new, unexplained category among them. And the instrument built specifically to settle the population question at galactic scale is now weeks from launch, not years. Nobody currently knows, with real confidence, whether starless worlds outnumber the planets still orbiting stars or fall meaningfully short of them. What the evidence increasingly suggests, cautiously and without overstating it, is that the answer is closer than most people assume, and that the galaxy's population of masterless worlds may rival or even exceed the population of worlds that still have one. There is something fitting about the timing of all this, even if it is only a coincidence of scheduling rather than anything deeper. For more than 2 decades, this entire field has advanced in short, uneven bursts. A discovery in the year 2000, a bold claim in 2011, a correction in 2017, a stranger discovery still in 2023, each one separated by years of quiet, unglamorous survey work in between. A single spacecraft already built, already tested, already sitting at a launch complex in Florida, is now poised to compress the next stage of that uneven progress into a handful of years. Whatever the true number turns out to be, it will not stay unknown for very much longer. None of this changes what any single one of these planets experiences, out there, right now, drifting between the stars whose light will never reach it in any meaningful sense again. Counting them tells you how crowded the dark actually is. It does not tell you what it is like to be the thing crossing it, alone, for longer than any number in this script has really tried to hold, or what becomes of a world like that once every question about its origin and its abundance has finally been answered, and there is nothing left to do but keep drifting. There is a narrow window, early in a planet's exile, when the isolation is not yet final. For the first several million years after a young star cluster forms, its members sit close together, stars and rogue planets alike, crowded into a volume of space small enough that paths still cross. Researchers Haggai Perez and Thijs Keuvenhoven modeled what happens to free-floating planets during this crowded youth, and found that if rogue planets were about as common as stars, somewhere between 3 and 6% of stars in that cluster would end up gravitationally capturing one, pulling it into a new, wide, looping orbit around a sun that never made it. A captured world like this settles in far out, hundreds or even thousands of times farther from its adopted star than Earth sits from ours, tilted, often backward, a stepchild rather than a native. It is not much. It is not even a home in any sense our own solar system would recognize. But for a small fraction of these worlds, it is something. That window does not stay open long, and it is worth sitting for a moment with just how young a cluster still is while that window remains. A few million years sounds substantial spoken aloud, but set against the age of the galaxy itself. More than 10 billion years, it barely registers, a single held breath at the very start of an otherwise silent, endless exhale. Every rogue planet that will ever find a new star finds it during that breath, or not at all. That window does not stay open. Star clusters are not permanent structures. Within roughly 100 million years, the gravitational tugging of passing stars, and eventually the pull of the galaxy itself, pulls a young cluster apart, scattering its members outward until they are no longer neighbors in any meaningful sense. Once that dispersal finishes, the odds of capture do not simply drop. They effectively end. A planet that leaves its cluster still unclaimed will spend the rest of its existence in the much emptier space between star systems, where the average distance separating one star from the next is measured in light years, rather than the astronomical units that once separated planets in a functioning solar system. In simple terms, every rogue planet gets one brief, crowded childhood in which belonging to something new is still statistically possible. Almost all of them pass through that entire window carrying nothing, and once it closes, it does not reopen. Whatever happens to a planet after that point, it happens alone, and it keeps happening alone, for longer than anything else in this script has really tried to measure. Consider what alone comes to mean once real distance enters the picture. In the neighborhood of stars like our own Sun, the typical gap between one star and its nearest neighbor runs several light years, a distance that light itself, moving as fast as anything can move, takes years to close. A planet drifting through that gap is not passing quickly between destinations the way a traveler moves between cities. It is crossing a nearly featureless stretch of dark that dwarfs anything in its own former solar system, at a pace that makes the word crossing feel almost too active for what is actually happening. There is no sensation of motion for a planet with no eyes and no reference point. There is simply position, changing with aching slowness against a backdrop of stars that do not visibly shift for spans of time longer than entire human civilizations have existed. And this is where the timescale of a single wandering planet starts to separate itself from everything else discussed so far in this script. A star's life, even a long one, is finite and countable in a way that feels almost comfortable by comparison. Our own Sun, for instance, has perhaps 5 billion more years before it swells, reddens, and eventually fades into a slowly cooling ember of its former self. A rogue planet has no equivalent deadline written into it. Barring a genuinely improbable collision or an equally improbable late capture, it simply continues, carried by momentum it was given once, long ago, during the single violent event that set it loose. The heat inside it will keep bleeding away. The radioactive decay this script described earlier will keep slowing, and if it happens to be one of the rare few sealed beneath an insulating shell of ice or a thick primordial atmosphere, an ocean somewhere inside it may keep existing, warm, dark, and utterly unwitnessed, for a length of time that does not map cleanly onto anything a human mind is built to hold. It is worth returning briefly and gently to that ocean if it exists on even a handful of these worlds. Nothing has ever seen it, no light has ever touched its surface, and by the nature of the planet carrying it, no light ever will. If there is motion in it at all, currents stirred by heat rising from below, it moves in a darkness so complete and so permanent that the very concept of dark stops meaning quite the same thing it means here. On a world where darkness is simply the absence of a sun that will rise again in a few hours. On a rogue planet, dark is not a phase. It is the entire and only condition, the whole of the day, every day, for as long as the ocean itself continues to exist. Set this against the length of a single human life, and the comparison stops being useful almost immediately. The way trying to weigh a mountain against a single grain sitting on its slope stops being useful. A human lifetime, generously measured, might span a single century. The radioactive decay quietly warming a rogue planet's interior operates on timescales in the billions of years, meaning that from the moment such a planet is cast loose to the moment its last meaningful heat finally bleeds away, roughly 100 million human lifetimes could pass in sequence, one after another, each one entirely unaware that the world in question exists at all. Civilizations could rise and end many times over on some other, luckier world, and the rogue planet would still be there afterward, unchanged in any way that mattered, simply further along the same slow, private countdown it started with. Somewhere in the galaxy tonight, hundreds of these worlds, perhaps many more, are doing exactly this. Not traveling toward anything, not fleeing anything anymore, since whatever violence set them loose finished happening millions or billions of years ago and has long since become irrelevant to their present condition. They are simply continuing the way a stone continues to fall long after the hand that threw it has stopped existing, indifferent to whether anyone is left to track its path. Some of them carry oceans. Most, almost certainly, carry nothing but frozen rock, and the last, faint traces of heat leaking out of their interior. Patient enough that faint and patient might, after long enough, come to mean the same thing. There is a strange kind of symmetry in this, one that has been sitting underneath the entire hour without being named outright until now. Every planet still orbiting a star, including the ones under your own feet right now, is, in a sense, on borrowed time in the opposite direction. It stays bound to its sun through mutual gravity, warmed and lit and organized by that relationship for as long as the relationship holds. A rogue planet has already had that particular arrangement end, or in some cases, never had it begin at all. What looks, from here, like a uniquely bleak condition, no sunrise, no warmth from above, no place in anyone's sky, is not actually the exception among planets in this galaxy. Given how the numbers in the previous section leaned, it may, when all of it is finally counted, turn out to be closer to the default. Isolation on a planetary scale may simply be what most worlds experience most of the time, and it is the ones huddled close to a star, lit and warmed and tracked by curious eyes on their surface, that are the genuine anomaly. That reframing does not make the condition any less severe for the world experiencing it. A planet drifting alone does not know it is common. It does not take comfort in statistics, or in the knowledge that somewhere, light years or millennia away, another world shares its exact predicament. Whatever heat it carries entirely by itself, for however long that heat lasts, against a silence that will not be interrupted by anything, except, perhaps, once in an almost unthinkably long while, the very edge of another star's gravity. Picture that single encounter, because for many of these worlds, it may be the only event of any consequence across their entire existence. A star, itself moving through the galaxy on its own long orbit, happens to pass close enough that its gravity reaches out and touches the planet's path, bending it very slightly, the way a stone dropped into still water bends the direction of a leaf floating some distance away without ever quite pulling it in. For a period that might last centuries, the planet is, in some small gravitational sense, in the presence of something again. Then the star continues on its own course, the distance widens, and the influence fades back to nothing. The planet is released, unclaimed, its trajectory only marginally altered, back into the dark it came from. No one aboard witnesses this, because there is no one aboard. No record of it survives anywhere except in the bent, barely perceptible curve of the planet's own onward path. A signature written in trajectory rather than memory. The only kind of history an object like this is capable of keeping. Multiply that single brief encounter by however many such worlds exist, scattered across a galaxy that, by the most recent estimates in this script, may hold as many starless planets as it does stars with planets still attached, and something closer to the true scale of this condition starts to come into focus. It is not one lonely world out there. It is an entire population living out some version of the same slow arithmetic, each one carrying its own private ration of leftover heat, each one following its own uninterrupted line through the dark, each one entirely unaware that the word alone is, for planets in this galaxy, closer to the rule than the exception. You have been listening to the story of a kind of world most people never think about. The kind with no sunrise waiting for it tomorrow, no sunset to close the day, no day to close at all. Somewhere out there tonight, one of them is passing quietly through the space between two stars whose light has nothing to do with it anymore. What a rogue planet really is turns out to be less a single answer than a condition, arrived at by more than one road. Some were built close to a star and then thrown clear of it, carried out by the same restless physics that shaped every planet in this solar system, including the one currently holding you up. Others were never close enough to a star to lose one, born instead the way a star is born, in a collapsing cloud of gas and dust that simply ran out of material before it could ignite anything. Both kinds end up in the same condition. Both kinds end up alone. And by the numbers, this galaxy is only beginning to take seriously. Alone may not be the strange outcome for a planet. It may be closer to the ordinary one. Why it wanders alone was never really a mystery waiting to be solved so much as a habit of language waiting to be corrected. Planets are supposed to have suns, the way rivers are supposed to have banks. But the universe does not owe its objects tidy relationships. It produces worlds, in whatever quantity gravity and chance allow, and only afterward do some of them happen to end up circling something bright enough to be called a star. The rest simply continue, carrying their own small private allotment of heat, asking nothing of anyone, expecting nothing back. You are not one of these worlds. You are sitting somewhere with a sky above you, a sun that will rise again within the day, gravity holding you gently to a planet that is, by the numbers, something closer to unusual. That is worth noticing before you drift off, not as a reason for anxiety, but as a kind of quiet, undramatic luck, the sort that is easy to overlook precisely because it has never once failed you. Somewhere in the dark tonight, a world with no name anyone will ever know is still moving, still cooling, still carrying whatever warmth it was given at the very beginning, toward no destination, on no schedule, answering to no one. And it will still be moving long after this sentence, and everyone who ever heard it has gone quiet,